right. How we doing? How we doing? All right, let's get started for today. Today's going to be a little bit of a practice day, getting ready for your quiz on Friday. We do have a lab tomorrow. And then that lab we do tomorrow, you guys at home will go ahead and do that lab next Thursday. So has everybody done their lecture questions? I went through, I see a few people that didn't get both of them done. So you want to make sure you go into your grade book and make sure that you see that both of the lecture questions are done, because we're going to be a little bit more of a stickler for turning things in on time this time. Quarter 2. Okay. So looking at the quiz for Friday, it's 9 questions and 30 points. 9 questions and 30 points. It will be over the 2 days of lecture we already did. So it's going to be over thermal energy, temperature, and heat. And then it's also going to be over endo, exo, entropy, and spontaneity, which is what we did yesterday. You guys will take it in class. Those of you that are physically here, those of you at home, you have to take it between 7:30 and 1:30. Okay? So that's what we're looking at. Shouldn't be too bad. Probably the harder stuff is going to be the second stuff here because it's never been done before. You guys probably know all about thermal energy, temp, and heat. So what I want to do is I'm going to spend a little bit of time going over some stuff. I don't think we did every single worksheet in here. So what we're going to do first, if you start with your packet open, not the first page, but the second page, here we go, a third page, excuse me. We're going to do the little scenarios. I don't think we had time to do those, so we're going to do those today. Let me give you an example. So this one isn't in your packet, so let's just watch. Sometimes students have a hard time drawing the heat diagrams, telling me which way energy is flowing, all that kind of good stuff. So I'm going to give you an example, then you're going to do 2 on your own. So we know that everything has to go from hot to cold. Everything goes from high to low, always. No such thing as cold applying to you. Cold is just a definition of removing heat from yourself. So it's starting to get cold outside, if you will. How does putting on a jacket keep you warmer? Does a jacket actually heat you up? Okay, what does it do? So if you were to draw a heat diagram for, how a jacket works, when you draw a heat diagram, you want to draw kind of what you got going on here. That's you. So much fun. Here's a little hat. Oh, you look good. Oh, there you are. Okay. When you walk outside on a cool day, are you warmer or colder than the environment outside? You're warmer, right? We'll say you're about 37 degrees Celsius. So you're the area of high energy. And outside, if it's a super cold day, it might be 5 degrees Celsius. That'd be about 38, 40 degrees. So that is the low energy. So when you go outside, everything goes from high to low. When you go outside, why do you feel cold? Which direction is energy flowing? From you to the environment, correct? So energy is leaving because everything goes from high to low, correct? Now, by putting on a coat, here's your nice fluffy coat. Has anything changed in the direction of energy transfer? No. You're still hot. It's still cold out. What is that coat? And I'm looking for a term. It might start with an I. What is that coat that you put on going to do? It is an insulator. Thank you. That coat is an insulator. So are you still losing energy to the environment? Yes, but you're just doing it slower. Okay, you know you can't stay outside forever in a coat. You're still going to get cold eventually. Okay, but that just slows you from losing energy. Okay. What is your coat usually made of? What are some materials your coats are made of? Cotton, wool, down, things like that. What would happen if you tried to make a coat out of like copper? Would that be an effective coat? No, because copper is if it's not an insulator, it's remember the word, if it's not an insulator, it's a conductor. Very good. And so you wouldn't slowly lose energy. You would be quickly losing energy to the environment, and it will cool you down really fast, okay? So what I want you to do, and it says Unit 3 Thermochem worksheet, thermal energy, temperature, and heat. there are two scenarios I want you to draw some heat diagrams for. Okay. In the morning, you walk into your bathroom and you step on the tile. How does the tile feel on your toes? Feels cold, right? And so what do? You jump onto the rug. What does the rug feel like? The rug feels warmer. Are they actually at different temperatures? Yes or no? And then I want you to go ahead and I want you to give me a Y. I want you to, and so just draw a little foot. If it was me, it would be like this. Here's my foot. Here's my foot. Here's some tile. Here's some rug. Tell me, where is the high energy located? Where is the low energy located? Which direction is energy transferring? So again, we're going backwards. We're only the third page in. And then at the very bottom, you can skip number 2 because I don't really care about conduction, convection, and radiation. So skip number 2. I want you to tell me in the next one, how does styrofoam keep things cold? If you had ice cream in a styrofoam cup, which direction is heat trying to transfer and all that kind of good stuff as well? Okay, so I'm going to come around, see how we're doing on this. Those of you at home, we're working on this worksheet. Again, it's just the third one in. Third one in. We went backwards a little bit here. Third one in. Those of you at home, talk to me. Do the first one and the third one. Let's do it. You figured it out. Perfect. Draw feet and some floor. Draw some feet and some floor. Those were test questions. How would you answer that? Beautiful. I see a lot of people working hard on that, doing good. All right, so let's do this first one, and then hopefully the second one can give you a little bit easier look into it. So the first thing you're thinking of, your body, again, is at about 37 degrees Celsius. Are you warmer or cooler than the ground in the morning when you wake up? You're warmer, correct? Now, these two things feel like they're at different temperatures, but are they actually at different temperatures? Unless you have the luxury of having heated floors, and then color me jealous. Are they at different temperatures, the floor and the rug? They are not. Okay, we'll say they're about, I don't know, room temperature, 26 degrees Celsius. Both of them are. Okay. Which direction is energy flowing? You are high, the rug is low. You are high, and the tile is low. So which direction is energy transferring? It's transferring from you to the rug and from you to the tile. Why does the tile feel colder to you? Why does the tile feel colder to you? Talk to me. We're looking for some terms. Okay, why does the rug feel warmer then? One of these is okay. Yeah, talk to me. The rug is an insulator. So therefore, it's trying to take your energy. It's like, give that energy to me. And it can't take your energy very, very fast. So therefore, it feels warmer to you. The tile's like, give me the energy now. Go, go, go. And it can take it much quicker. So they're not at different temperatures. Very important. They're not at different temperatures. It's just one can take and give energy faster because it is a conductor. Okay, so you might see a scenario like this on your quiz on Friday where you have to talk about what's a conductor, what's an insulator, which direction energy is transferring, what is high, what is low, all that kind of good stuff. Okay, making sense? Awesome. So I'm skipping number 2 because conduction, convection, and radiation is very simple. Okay, and you guys probably did it at middle school. So this says, how does styrofoam keep cold things cold? I understand how it keeps coffee hot, but how does it know to keep ice cream from melting? So what I want you to do is I want you to draw 1 cup with hot coffee in it and tell me the direction of energy transfer. And I want you to draw 1 cup with ice cream in it. And I want you to tell me the direction of energy transfer. And then I want you to talk to me about what styrofoam is and what it does to the transfer of energy. I'm going to give you 3 minutes. If this was a test question, how would you answer it? This was a test question. How would you answer it? 1 cup, where is high, where is low? Direction of energy transfer. Another cup, where is high, where is low? What is the direction of energy transfer? Awesome. Perfect. If this was a test question, how would you answer it? Perfect. Get some highs and some lows for me there, buddy. What? Yeah, I did. Unfortunately. It was staying for a minute. We're good, though. Thank you. All right, so let's get into it. Hopefully, we're feeling swell. When you have a cup of hot coffee, is the coffee at a higher temperature or a lower temperature than the outside? High. And that means the temperature on the outside must be low. So your hot coffee does what? It cools down over time because energy goes from your coffee to the outside. Now, the reason why you don't drink coffee in like a metal cup is because if this was metal, would that go slowly? That would go quickly. So styrofoam is called a what out of our terms? Styrofoam is an insulator. And so does that speed up or slow down the direction of energy transfer? Does an insulator speed up or slow down the transfer? Slows down the transfer of energy. Does that make sense? So the question here is, well, then how does a styrofoam cup work? And the most incorrect answer, I will tell, Mr. Campbell just yelling at me. The most incorrect answer is that people go, oh, so it's cold on the inside, and that just keeps the cold right on in there, doesn't it? No. Okay. That's not the way that things work. We know that it's low on the inside and it's high on the outside. How does that ice cream melt? It has energy that tries to come in and melt it. But can the energy get in very quickly? No, because you have your insulator in the way. This is where people get confused. They say, oh, it's just going to keep the cold inside. There's no such thing as keeping cold inside. Okay. What it's doing is it's keeping the heat out. So the next time your parental unit yells at you for, you're letting all the, cold air out, or what, you're letting the heat in. Okay. Accidentally, you keep the door open. Okay. So perfect. So you will see some of those scenarios on the quiz on Friday. I want to make sure you know how to do those. We're feeling good. All right. So the next thing I want to do is we're like skipping all around in here today. In your packet, let's change 1 page. That was the notes yesterday. 2 pages, that's the worksheet we're going to do. But let's go another 3 where it says thermochem, endo, exo, and entropy recap. I just want to go through this one more time. If you care, those of you at home, there is one more bell work we're not going to get to, and I have the key in the Thursday folder. But you guys here in class, you're going to do this bell work either tomorrow during the lab or Friday right before the quiz. Okay, so there is one more practice worksheet in the packet if you would like to practice it before the quiz on Friday. All right, so let's do this. Which direction is energy transferring in an endothermic reaction? Endothermic. Is it going in or out? Endothermic. In. Okay. So you can just write in if you would like. In an exothermic reaction, energy is going out. So what I want you to do is I want you to think, and I'm going to give you 30 seconds of music so you can think about it. I want you to try to label number 2. Which has you gaining thermal energy from the beginning to the end, and which one has you removing thermal energy from the beginning and to the end? You have 30 seconds. One of these is endothermic and one of these is exothermic. Take a look at the graphs and everything in there. Think about it. Answer that next question, number 2. Label one of the graphs endo and one of the graphs exo. What do you think? What do you think? Wonderful. All right, let's take a look at it. In this first one, I have more energy at the beginning and less energy in my products. So I have released energy. Is that endo or exothermic? Exothermic, very good. And if it says Y, less energy at the end. And this one, my products started with a little bit of energy and I ended up with a whole lot more energy. So this is actually going to be taking it in endothermic. We end up with more energy at the end. Right. Yesterday, we talked about entropy. And entropy is the measure of disorder or chaos or randomness in a system. Chaos, randomness, disorder in a system. So remember we had our boxes. And if you guys can kind of commit these to memory or at least know how to use these, what had the lowest entropy, or if you want to write this here, lowest disorder? You got it. That is a solid. So all I would do is take a box. And this does not have to take very long. Solid. Okay. Everything's where it needs to be. A very low amount of randomness or disorder. After a solid, liquid. You got it. In a liquid, they just kind of go a little bit more wherever they want. Little more disorder, things are moving around, a little more random. Before we get to gas, there is actually something else. If I have a liquid, good. And then I add more stuff into it. So like, let's say I have a sugar solution, or I have a can of pop, or I have, you know, stuff mixed in something, lemonade. That's called an aqueous solution. Oh, is that the one that's been annoying me? Giant cricket. Big cricket right behind you. He's going for your book bag. You're okay though. You might want to just give him to Mr. Campbell. He probably is meant for a snack for one of his animals. You want me to pick it up or kill it? I mean, you can do whatever you want, poor cricket. He's going to die either way if he gives it to me. Okay, well then just smoosh it. Sorry. Okay. And all right, I'll do it though. That's nice. Yeah, there's a cricket. It probably came out of Mr. Campbell's classroom. If y'all have had Mr. Campbell before, you know, just bugs come out of his room. That's okay. He'll be appreciative of the cricket coming back. And then once we get to the highest, there is a gas. And gas particles go wherever they want, however they want. Very, very, very high disorder. Okay, very good. So what I want you to do is a few steps here. When you're going to make Kool-Aid, okay, so you have a pouch of the Kool-Aid powder, solid, liquid, aqueous, or gas, the Kool-Aid powder. Which one is the powder? The powder is a solid. Okay, so we're going to get there. Yeah, starts as a solid, and then once you make your Kool-Aid, it goes to an aqueous solution. So the question says, is it more or less disordered? If I go from here to here, are we becoming more disordered or less disordered? More. Okay, I want you to do the next form. Taking a popsicle. So I'm taking the solution and I'm freezing it, cooling an iron into a nail, burning a candle, putting an Alka-Seltzer tablet. If you don't know any of these, we can talk about it. But I want you to think, how are you sliding on this scale? I'll give you 30 seconds for each. So ready, set, see if you can't write more or less disordered for me. And you will have to do these on the quiz. So do go ahead and try them, please, please, please. Please try these. And if you just want to write more or less, it doesn't bother me. This is your practice. More, less, more, less. All right. I see everybody's trying them all. Let's do it. Freezing a popsicle starts as a solution and it goes to a solid. So that is becoming less disordered. Molten iron into a nail. Molten iron is a liquid. A nail is solid. So that is also less disordered. Burning a candle. Burning a candle is a solid. You either get the wax to go into a liquid or you also get gases out of a candle. Either way, the disorder is increasing, more disordered. And does everybody know an Alka-Seltzer tablet? It's like a little solid thing. You put in water. What happens when you put it in water? You see bubbles, it dissolves, and you see bubbles. So you take your solid and you go to an aqueous solution, or you also go to a gas. So that is more disordered. Okay? So you will see some of those on your quiz. Everybody feeling good on that? Let's talk about the chemistry way you'll see it. So the next one, it says, is the entropy increasing or decreasing in the following chemical reactions? Take your pencil, draw a little line right at the arrow, and you want to look at what happened at the beginning and we'll look at what happened at the end. We have a gas and a gas, so I'm starting here, goes to a liquid. So you have to look overall, okay? Gas goes to a liquid. Is it increasing entropy or decreasing? That's decreasing. Okay, this one, I'm going to draw an line my arrow. I have a solid and aqueous going to an aqueous and a gas. So this really isn't moving, okay? So what I'm going to focus on is the one that is moving. I see a solid to a gas. So talk to me about that. I'm going to give you another 30 seconds. Answer those. Answer those. Yeah, talk to me. Okay, we're going to get to one place where we're just, if that is what you need to do, you need to do. You're doing so good with this review. Okay, all right.
Cricket's okay, everyone.
The cricket's okay?
It's out in nature now.
Oh, that's nice.
Campbell said we do not want
to feed it.
He said it has disease.
Might have disease. I was thinking about that, but I didn't know if it was his or not.
Why?
They were asking at home if there's a cricket. So everybody at home, the cricket is okay. It is outside, living its best life. Just not in here. It was a big cricket. It could jump very high.
Crickets in my backyard.
They're not that big? All right. So the second one, we have a solid to a gas. So the entropy increases. I see a gas and a solid going everything to a solid. So that's going to decrease. I see a liquid and a gas going to a gas and a gas. So I'm talking increase there. Everybody feeling good? You can do that on a quiz on Friday as well. Say, get this entropy out of here. It's so easy. All right. The last hard thing, we're going to put it all together. A spontaneous reaction occurs when it happens on its own or there's no outside help. However you want to remember. Remember, when I'm lighting my candle here, I have to get it started, which is fine. But then as soon as I stop, is now this reaction going by itself? Yes. So this is spontaneous. It just goes. There are two things. Who can tell me if they remember what two things you have to have? You have to have at least one of them to be spontaneous. Anybody remember one? You have to, what do you have to do with your energy? It has to go out. So it needs to be what? Exothermic. Thank you. And thank you. And increase in entropy. If you get one of those, you are spontaneous, okay? So let's do this first scenario. You are going to see things like this, and I think this is going to be the hardest thing on the quiz. You're going to see things like this on your quiz. Ready? Imagine you're sitting next to a fire on a cold winter night. Sitting next to the fire. How does it feel? When you put your hand next to a fire, you probably feel warm, right? Hot. Here is your reaction. You're going to take wood as a solid. You're going to burn it. You're going to get some solid wood. You're going to get a gas and a gas. I'll help you with the first part. Is the fire burning? Once you get that log starting to burn, is it spontaneous? Yes. It goes on its own, correct? So we're going to say yes because it goes on its own. Now, what I want you to do is I want you to circle 4 things. I want you to tell me, remember you said you can feel heat. Is the energy going in or out? So is it endo or exothermic? Looking at your reaction, what's happening? So you can say it goes from here to here. So is the entropy increasing or decreasing? And then so it must be spontaneous due to one, the other, or both. I'm going to give you a minute. I'm going to walk around. This is how the harder questions will be on your quiz. Let's do it. What are we thinking? What are we thinking? And this is just practice, so please give it a try. Nice. Yeah, yeah. That's spontaneous. Tell me why. All right. Spontaneity, putting it all together. This is the harder stuff. And you will see 2 of these scenarios on the quiz. So this is coming at you. So if you can do these, you're feeling good for the quiz. All right, let's do it then. All right, ready. So I have a fire. Thank you. You're standing next to it. And you feel warmth coming from the fire to you, correct? So for the first one, is energy going into the reaction or coming out of the reaction? Going out. Oops, that is a high. So is it endo or exothermic? Exothermic, beautiful. I see it goes from a solid to a solid with 2 gases. What's happening to my entropy? It's going from a solid to a gas. My entropy is increasing. So why is that fire spontaneous? Both. Does that make sense? Feeling good. Let me give you a harder one. This one is much more challenging because people don't want things to be the way they are. All right, so now I have some, just going to put it right on here. I have some liquid wax here. I want you to think about the temperature of it while it's a liquid. Okay, I'm going to take this liquid wax and I'm going to pour it out onto this other one, and it's going to cool. What is going to eventually happen to that liquid wax? Is it going to cool and harden? Am I doing anything to it? Okay, what I want you to do, and this is a little bit of a harder one, I want you to then answer the rest by yourself. Is it spontaneous? Yes or no? Because it's going on its own or it needs help. I want you to think it is cooling down. Okay. Does energy need to go in or out of it? Is it endo or exothermic? Think about what's happening to the entropy. And then you guys can tell me the spontaneity of it, okay? And why. This is a hard one. Let's see if you can do it. See what we're thinking. Beautiful. This one's a toughie. Does it have one by itself? Yeah. Mm-hmm. disorder. All right, let's give it a try. This is a tough one. Oh, God. Couldn't get everybody. Okay. Fine. Maybe it's not that hard. Okay, I see you. All right. So, all right, here we go. So the thermic nature of this is the one that always gets everybody. It makes it hard, but that's okay. We can do this. So, is the candle wax hardening by itself spontaneous? The answer to that is yes, because it goes on its own again. Okay. Now, if I have liquid wax, do I need to put energy into it, or do I need to take energy out of it to get it to cool down? Out. Okay, you have to take energy out of it. The particles are sliding around. In order to make it a solid, I need to slow them down. It cools down. It releases its energy to the outside as it cools. So energy is going out, and this is so tough. So it is exothermic. I saw a couple of you that had that. That is beautiful. Okay, that's tough. A lot of people want it to be endothermic, and I get it. I get why. But it is actually cooling and releasing energy. The only problem is it was a liquid, and now it is a solid. So what's happening to my entropy? It is decreasing. So is my entropy helping my spontaneity? No. What is the only thing making that spontaneous? The fact that it's exothermic. Okay? Does that make sense? We feeling okay? All right. So what I do have here is, you're like, oh, no, I'm sick of doing it. What I want to do is if you go backwards, again, I said we're going backwards today. That was the recap. I have one more practice worksheet. And if you feel good on the front, why don't you just flip it on over to the back? Boop, boop. Okay, I don't know why all these blue lines are there. There we go. So what you're going to do, I'm going to show you at home. Yeah, all you do is you take your hands on it. There's a little coin. Can you get your hands? Perfect. Can you get your hands on the little coin? You don't have to bend it hard, like you're not trying to break it. Just bend the little coin a little bit. We'll make like a little snap. Oh, you just have to kind of move it a little bit. And then you'll start to see a reaction. Hopefully those of you at home can see it. How does that feel? It feels warm, right? So as that reaction is happening, it is now extremely warm. What you can actually do is you can boil it. So it's losing all of its energy. Okay. If you boil it, puts the energy back in, puts it back into a liquid, boom, you have it again. Okay. So let's talk about it. You're holding it. The process that Snap Heat Pack goes through, is energy going into it or is energy coming out of it? Coming out. So is this an endo or an exothermic reaction? Exo, and I think I have my circles here. Okay, but let's look at the entropy. It started as a liquid, correct? And now it is a solid, liquid to solid. Is my entropy helping? Because as soon as you cracked that, did you have to do anything to make it go? It just went. Okay. So my entropy is actually decreasing. So the only reason why this thing is spontaneous is why? It is exothermic. Okay. Sorry you guys at home can't feel it, but it is nice and chilly. That's fun. I mean, warm, chilly, warm. I'm thinking about the next one. Okay. Nice and warm hot pack here. I guess I should have given you a thermometer before. I'm probably going to give you a thermometer for this one because these is hard to understand sometimes. You had these in your old school?
Yeah, in California.
All right. So what you guys have is called a cold pack. Inside one of these cold packs is what's called ammonium nitrate. Okay. Ammonium nitrate. And ammonium nitrate here is a solid. And what that solid's going to do is it's going to mix with a liquid. So what about temperature do you have for your pack here? Those of you at home, here we go. Full pack. I'm looking at about 23 degrees. You're in the 20s.
I'm in
21. Okay. Now, so we're in the 20s. I want you to take your pack, and there is a little thing of water, like a little pouch. You actually want to squeeze it. So it says squeeze together here until it pops. Then you want to shake it. And you're going to mix that ammonium nitrate with, good, the water. How does that feel? That probably feels what? Oh my God, I thought we had 5 more minutes. Sure. The temperature is going down, so it's endothermic. Okay? Perfect. If you'll leave your packs behind for me, we'll pick this up tomorrow. Those of you at home, you can finish this worksheet. I'll put the key online, and there's also another bell work as well. I guess I thought we got out of here at 55. I'm sorry. Go ahead and leave those packs behind, please. Perfect. So this is an endothermic reaction. It's taking energy from your hand, putting it into the reaction itself. You're like, I prefer the hot pack. Thanks. Good stuff, guys. Good stuff.